Hello everyone, welcome to this week's Crunch seminar. Today we have two talks. For the first talk, Dr. Francesco Regazzoni would be presenting his recent work on shape-informed operator learning for non-intrusive mesh-free surrogate models. Francesco earned his PhD from Politecnico di Milano under the supervision of Professor Alfio Quattroni. He has held visiting scholar positions at INRIA Cercle de France, Pennsylvania State University, and Harvard University. Currently, he is an associate professor in numerical analysis at Politecnico di Milano. His work has been recognized with several international awards, including the ICOMA's Best PhD Thesis Award, the VPH Young Investigator Award, the SIMAI Young Researcher Prize, and the Odin Hughes Award. His research interests lie at the intersection of machine learning and scientific computing, with a particular focus on dynamics discovery in latent spaces and shape-dependent surrogate modeling. He is also interested in the numerical approximation of multiphysics problems, especially in the area of cardiovascular modeling. With a short introduction, I invite Dr. Regazzoni to present his work today.
Thank you very much. Thank you for the kind introduction and thank you for having me. First of all, I'd like to acknowledge my co-authors. What I'm going to present is the result of the work of several people that you see listed on this slide. So let me start with the motivation behind this work. Let's consider what's the traditional modeling and simulation approach in computational sciences, and in particular in biomedicine, that is my favorite field of application. So we typically start from images, medical images, we do segmentation, we generate a mesh, and then we exploit the knowledge of the physical processes encoded into mathematical models and numerical approximation to perform numerical simulations that can be useful for several tasks. What are, however, here the bottlenecks? The first bottleneck is in the pre-processing steps that are time-consuming very often and also difficult to automatize. And the second bottleneck is the computational cost of running the simulation. So we all know that running simulation on real-life problems very often requires hours, even on supercomputers. It can cost a lot of money because of electric power consumption, and it's also not sustainable from the environmental viewpoint in many situations. And this is even more true if you consider that very often we need to run the model several times, for instance, for optimization or for doing uncertainty quantification. And for these reasons, operator learning can be used to build surrogate models that overcome these inconveniences by bypassing the mesh generation steps and also by lowering the computational costs of running simulations. And before digging into methods to derive surrogate models, let me briefly define what we mean by surrogate model. So the starting point is a physics-based model that can be seen as a map going from some space of input to some space of output. So the inputs can be scalar parameters, functions of space, or even shapes, and the output can be scalars, functions, or whatever. Then the first step is to approximate numerically the physics-based model by obtaining what we call the high-fidelity solver that can be based on finite elements or finite volumes or other discretization methods. Then we sample the space of inputs and we collect through the high-fidelity solver the high-fidelity solution, so the corresponding solution. And these form the training data set for operator learning. That is nothing but the standard supervised learning framework where we select a training data set, an hypothesis space that is a subset of all the possible functions mapping input to outputs, and then we look for the model belonging to this hypothesis space that minimizes the mismatch between the data and the model prediction. This is called training, and the result is the surrogate model, that is a model that is typically approximate, but much faster than the high-fidelity solver. And is it worth to construct a surrogate model? Well, I think that this is not always the case, but there are situations where it is. The first one is that we need a real-time solution. For instance, if you want to assist robotic surgery, or you want to perform real-time control of some plants, then no matter how expensive it is to construct the surrogate model, but then it is worth it because you need solutions in real time. And the second case is when you need to query your model several times. For instance, you want to perform parameter sweeps or optimizations. And in this case, suppose that you need to do n query evaluations, then if using this high fidelity solver, then the total computational cost will be given simply by the product between the number of queries and the time required for a high fidelity solver run. Instead, by using the surrogate model, we need to generate the training set, perform the training, and then we have an online phase that is typically very cheap. And by this simple inequality, we can conclude that for a surrogate model to be convenient, we need that the number of training samples be much smaller than the number of queries that we need to run online. And this is the base of the sustainability of surrogate models, and I think this is very often overlooked in applications. And the main take-home message that I would like to propose is that a surrogate model that is good one is the one that is able to generalize well, even with a small number of training samples. And a situation when it is particularly challenging to generalize with a small number of training samples is when the shape of the domain can vary from sample to sample. So this is what we call the shape-dependent operator learning. And the point is that most operator learning methods are designed to work on a fixed domain. But what happens when we move to multiple domains, like it is often the case in biomedicine, where we can construct a surrogate model on a given patient, but then we want to use it on a patient that we have never seen before, and the first thing that varies is exactly the anatomy of the patient. So here the challenge is how to generalize in a zero-shot manner to domains that we have never seen. So standard approaches in computational sciences are based on the idea of deforming a predetermined mesh. And there are several methods to do that, like freeform deformation, radial basis functions, or even isogeometric analysis, statistical shape models. But what are the limitations? So first of all, if we have large geometrical variations, then we can have severe element distortions, or the problem can become ill-conditioned. If, in the case that we even have a variation in the topology of the domain, then we cannot find a smooth deformation from a template geometry to another. So there is not possible to find a point-to-point correspondence between geometries. And most of all, very often, the mesh is not even given a priori. So very often the domain is provided in a more general way, for instance, by means of just some points, cloud of points. So we need methods that are able to handling in a flexible way different representations of the geometry. So we need meshless methods that are not constrained on a predetermined discretization, on the predetermined grid, and that are able to handling flexibly different representation modalities of the geometry. So think, for instance, of point clouds. And with this motivation in mind, we proposed an architecture that we call USNets, Universal Solution Manifold Networks, in the sense that it learns the solution manifold of a PDE in a universal way with respect to the geometry. So this is the framework that we consider, that we have a full order model that is some partial differential equation, parameterized by some parameters, and defined on some domain. So to stress the dependence of the solution on the shape and the domain, we'll use this syntax. And we designed this architecture in this way. So first of all, everything is based on a neural field that is a neural network that receives the physical coordinate, so the space coordinate as an input, and outputs an approximation of the solution of the PDE in that point. So the neural network do not provide one shot all the solution on a grid of points, but need to be queried several times for each point where you need to know the solution. So in this way, we can fit just one solution. So to go from this to multiple solutions, we will condition a neural network on the physical parameters. And then we will condition a neural network also on what we call a shape code, that is a finite dimensional, hopefully low dimensional latent code that represents a domain. So we need to define a domain encoding function. It is a function taking as an input a domain and outputting the corresponding shape code. Of course, we need to find a way to define it. So for the moment, let's suppose that we have defined it, then we can train our usenet simply in a supervised way manner, simply by minimizing the mismatch between data and neural network prediction. And in order to improve generalization, we can pre-process the space coordinates by means of what we call the universal coordinate system, that is a function that maps any given geometry into a template geometry and provides to the neural network the coordinate in this template geometry, so in this universal coordinate system. And as I will show you, this allows to improve generalizability. So how can we construct such a domain encoding function? So how can we encode a computation domain that is an infinite dimensional object into a small number of parameters? So the first case is when we have a parameterized domain, which is very often the case in industrial design. So in that case, we'll just use the parameters. Or in other cases, we can use some landmarks that are coordinates or key points of interest. And for instance, in anatomy, medical doctors are used to define this kind of landmarks, so you can directly use them. Or you can think of automatically extracting some shape codes. A way of doing that is by using statistical shape models. That is to say, you find a point-to-point correspondence between geometries, then you perform PCA, and then you take the first n principal coefficients. Or, as I will show you later, we can even think of learning a shape encoding, and this will be the subject of the second part of this talk. But for the moment, let's consider the simple case of landmarks, and I'll show you this test case that is a blood flow in a bifurcating domain. So we consider bifurcating domains like the one that you can see here. They are synthetically generated by varying several parameters like the angle of between the two branches, the amplitude, the width, and also the presence of stenosis that you can see, for instance, here, that can impact dramatically on the blood flow. So first of all, we need to define a universal coordinate system, and to do that, we solve two simple Laplace problem on the domain, where we put boundary conditions at the inlet and the outlet such that the two solutions provide a top-down coordinate and a left-right coordinate. So in this way, we can represent each point on the domain into this abstract domain that is a trapezoid that allows to map each point to the corresponding point of another domain. Then we need to encode the domain in some way. So here we decided to use the landmarks, and we consider two situations. The first one with 26 landmarks, so all the points that you can see here, so a quite accurate representation of the geometry, and then just 6 landmarks, the orange ones, that of course provides a partial description of the geometry. And here the point is that we wanted to stress test the method to see how can it generalize by observing just 6 points. And then as a loss function, we use a goal-oriented one in the sense that we don't just fit the velocity vector, but also the direction of the velocity vector in this smoothed version in order to provide regularity. And here the point is that small vortices are not captured by the first term. So in this way, we can capture well both the regions of high velocity and the regions of small velocity. So these are the results. On the left, you can see testing geometries. So geometries not used during the generation of during the training. And on top, you see the finite element solution, and on the bottom, the neural network solution that can be obtained at a fraction of the time of the finite element solution. And you can see that the root mean square error by using 26 landmarks is of the order of 2%. And instead, using just 6 landmarks, it increases, but it increases just mildly, just 2 or 3%. So the method is quite robust to an incomplete representation of the geometry. And by using universal coordinate systems instead of physical coordinates, in both cases, we can increase accuracies. And to understand why universal coordinates allow us to improve the generalization, we can start from this observation, that is, the domain encoding function is never injective. And this is a consequence of the fact that shapes live in an infinite dimensional space, so it's not possible to represent them exactly with a finite number of parameters. So you can always have two geometries, like the one that are in this slide, that share the same shape codes. So in this case, share the same landmarks, these 6 points, but they are different. And you can see here and here, for instance. So what happens? This is the finite element solution on the first line, And if you use the physical coordinates, in each point in the physical space, the surrogate model will receive exactly the same inputs. So the output will be always the same. So we can do, of course, an error even or in one case or in the other. So we can generalize in both cases. Instead, by using universal coordinate systems, we are using a coordinate system that is better, that has a better adherence to the geometry. And so in this way, we can generalize better. Okay, so as promised, there are also ways to learn shape encoding. So far we've used the manually defined shape encoding, but there are also ways of learning a shape encoding, and I'm going to show you a couple of them. This first one is based on conditional neural ODEs, and this has been just accepted for publication, and the main author of this work was Riccardo Tenderini. And so here the idea is to use autodecoder stationary vector field diffeomorphism to map a template geometry to a target geometry. So the idea is that we have a neural ODE, that is an ODE system where the right-hand side is represented by the ODE, that learns how to map any point in the template geometry to the corresponding point of a target geometry. So by evolving this pseudo time from 0 to 1 simultaneously for all the points of the geometry, we can deform, by means of a smooth diffeomorphism, the template geometry to a target geometry. So this way we can consider one geometry. So how can we pass from one geometry to many geometries? Well, we will condition the neural network on some latent code that we will call the shape code. So a code that identifies a given domain. And a nice feature of this approach is that we can reverse time. So simply by switching the sign of the right-hand side of the ODE, we can run the diffeomorphism from the target geometry to the template geometry. So we can go backward in this pseudo time, so we can have the inverse map from the target to the template geometry. And this provides a universal coordinate system, so a positional encoding from each geometry to the template geometry. And how can we train this kind of model? So we train it by using an autodecoder approach. That is, we don't have an encoder encoding a geometry to the corresponding shape code, but rather at training time, we learn the shape codes associated to all the training geometries. So in other terms, we simultaneously optimize for the neural network weights and for the shape codes associated to all the geometries. So how can we find a shape code that is associated to a geometry that we have never seen before? So remember that we have just the shape codes associated with the training geometries. Well, the idea is that we will look for the shape codes such that if inputted to the model, this will lead to a deformation that leads to a geometry that is as close as possible to the target one. So in other terms, we will solve another optimization problem where the loss function is the same that we used during the training, but where now the neural network is fixed. So the neural network weights are freezed, we are just optimizing for the shape codes. So this is a very lightweight optimization problem that can be solved in a quick way, and this provides a way of associated a shape code to a given geometry. So we applied these methods to a dataset of 20 healthy aortic anatomies coming from the vascular modeling model repository. And in order to augment them, we generated, by means of geometrical variations, many other geometries in order to have a data set of nearly 900 geometries. Then we increased the number of shape codes, and we found that the optimal value was nearly 2 to the power 8. And this is a representation of the latent space that we found. This is projected on the first two principal components. And you can see a star for each of the training geometry, a dot for each of the augmented geometries. And you can see here the effect of doing interpolation, even either in a linear way or in a spherical linear way. And you can see that by doing interpolation between two existing geometries, we can get a quite nice smooth transition between one geometry to another. And this model can also be used in a generative modeling way, simply by sampling randomly a shape code by observing the empirical distribution of shape codes and by running the diffeomorphism to map the template geometry into asynthetic geometries. And in this way, we can get many realistic geometries. However, a limitation of this approach is that it does not allow for topology changes, since it is based on the idea of mapping, of deforming a template geometry into another one. However, we considered also another approach that is more flexible in the sense that it also allows for topology changes, that is instead based on the idea of representing the geometry through the associated sign distance function. So the point is that given a geometry, we can always associate a sign distance function, that is the function that has as a value, as an absolute value, the distance from the boundary, as the positive sign is the point is inside, the negative sign is the point is outside the geometry. And there is a one-to-one relationship in the sense that given a geometry, we can find a sign distance function, SDF, and given this SDF, we can recover the geometry simply by taking the zero-level set. And this idea has been exploited in the computer vision community since a few years by means of an architecture that is called the deep SDF. The deep SDF is another neural field, so a neural network that takes the space coordinate as an input and gives as an output an approximation of the sign distance function at that point. And the deep SDF is conditioned on a latent code that is associated to each or to any possible geometry. So each geometry has its shape code. How is training performed? So training, again, is performed in an autodecoder way. So at training time, we associate a code, a latent code to each of the training geometry. And at training time, we learn the training codes simultaneously with the neural network weights. And then at inference time, when we have a new geometry, we will look for the shape code such that if inputted to the neural network SDF model, this will output as SDF function that is as close as possible to the sign distance function associated with the desired geometry. So at any time we get a new geometry, we need to solve this optimization problem that is, however, very lightweight because we are optimizing a very small dimensional space, that is the space of shape codes. And very often we can even use a second order optimizers that are very fast since we have just a small number of variables. And solving this inference problem defines exactly what we before called the domain encoding function. So the domain encoding function consists in solving a small inference problem. So this allows to use this machinery within our USNet architecture. And so now I'm going to show you the results by applying this technology to the previous test case to the Navier-Stokes equations in the bifurcation. So on the left, you can see an example of the sign distance function. And on the right, you can see the chamfer distance that we get by reconstructing the geometry and increasing the number of dimensions. So first of all, what's the chamfer distance? The chamfer distance is a way of measuring the distance between two geometries when we have a different number of points representing the geometries. And the idea is very simple. You take each point of one geometry and you measure the distance from the closest point from the second geometries, and then you sum over, or better, you take the average of all the points, and then you do the same by switching the role of the two geometries. So here you can see that by increasing the number of the shape code dimension, the chamfer distance decreases, and it saturates when we reach 11. And 11, by the way, was the number of parameters that we varied to synthetically generate the data set of shapes. So here we have a saturation of the error when we hit the intrinsic dimensionality of the dimensional space, of the space of shapes. So this means that we were able to find some encoding that is somehow equivalent to the one used to generate the geometries. So by increasing the number of shape codes, as you can see, also the accuracy of the surrogate increases. You can see that the error gets lower and lower, both in the pressure and in the velocity. And by comparing it with the results that we got with landmarks, you can see that we can outperform landmarks, especially when we supplement also to the surrogate model the distance function. That is a way to provide positional encoding, by the way, so it allows to generalize better to new geometries. And so we can conclude that this automatic way of extracting shape codes is not even convenient with respect to the manual one, because we don't have to do it manually, but it is also more efficient in extracting geometrical features. Then, as a second test case, we consider this a perforated plate that where we apply some traction, and we would like to predict the deformation field, and we randomly vary the position of the holes and also their radius. You can see that we can get quite accurate results, and most of all, this is an interesting test case because here we have an explicit parameterization of the geometry that is simply the coordinate of the centers of the holes and their radii. So we can benchmark the accuracy of the surrogate model when we provide the explicit parameters, so an exact representation of the geometry and the shape codes. So a representation of the geometry that has been automatically learned and automatically extracts. And you can see that we can get almost the same accuracy, meaning that our shape encoding technique is very efficient. And in this case, we also compared with a popular approach that allows to generalize from one geometry to another that is based on graph neural networks, so in particular mesh graph neural networks. And you can see that our approach is more accurate. And if you increase the number of message passing layers, you can decrease the training error of mesh graph nets. However, the test error increases. So mesh graph nets are apparently more prone to overfitting. And so our interpretation is that they are more data hungry, in the sense that with the same number of training samples, our method is able to provide better accuracy while using a much smaller number of trainable parameters. Then going to an even more challenging test case, we can also vary the topology of the domain here by varying the number of holes. And you can see that also in this case, we can get slightly smaller but comparable accuracy that what we can get with an explicit parameterization of the domain. Now I'm going to show you an application to cardiac mechanics. This is still a work in progress, but we are in a good stage. And this is mainly done, was mainly done by Davide Carrara and Marcus Vogel. So what's the physical problem that we are aiming to solve? We would like to surrogate a passive inflation of a left ventricle, of a human left ventricle. So we apply pressure at the endocardium of the ventricle, spring boundary condition the epicardium, and then we look for the equilibrium configuration by using nonlinear elasticity and an anisotropical Zapffe-Ogden constitutive law that is a highly nonlinear constitutive law that accounts for the presence of cardiac fibers. And the typical features of the solution is that we have large deformation and a cross-sectional twisting that makes it particularly challenging. But here the goal is to predict the equilibrium configuration of a geometry that we have never seen in a parameterized way with respect to the endocardial pressure and to the stiffness of the tissue. And before going to the real geometries, we wanted to test the method on a more controlled case, so an idealized test case where we generate synthetic geometries by varying the long axis length, the short axis diameter, and the wall thickness. And so we trained a shape model, as I told you before, so in an unsupervised way, where we automatically extract shape codes. And then also we train a shape model where we provide the exact parameterization. So we provide the 3 parameters that we use to generate each geometries. And you can see that in the 2 cases, we can obtain almost the same accuracy. So we can conclude that the learned shape codes provide an almost perfect, or let's say an equivalent parameterization of the geometries. And since here we are in a low-dimensional space and we do have an explicit knowledge of the exact parameters, we can also try to provide some insights, so to gain some interpretability onto the latent space by plotting in the latent space the value of the exact parameters. So here the color codes corresponds to the 3 coefficients, long axis length, short axis diameter, and wall thickness. And you can see that there is a quite clear relationship between shape codes and the parameters that was used to generate the geometries. And going to the physical surrogate models, again, considering this idealized test case, we consider the 2 physical inputs that I mentioned before, that is the tissue stiffness and the tocardal pressure. And as an output, we consider the displacement field. So here, for simplicity, we consider an isotropic material, 36 training geometries, and 6x6 combinations of stiffness and pressures. Here you can see several testing geometries, so geometries that were not used in doing the training. If we don't use any geometrical information into the surrogate model is not capable of generalizing well to geometries, or fitting, or in general is not even able to fitting well training geometries. Instead, if we provide shape codes, we can get accurate results that are almost as accurate as in the case where we provide the exact parameters. So short axis length, long axis length, short axis radius, and wall thickness to the surrogate models. And so here each rectangle that you see is a different geometry, and each subrectangle is a pair pressure and stiffness. So by the way, you can see here that the larger error is when you have high pressure and low stiffness. That means very large deformations. That is the most challenging situation to learn. So now we can pass to the human geometries. And we had at our disposals a data set of 44 geometries coming by, obtained by merging 2 different cohorts of 24 pathological and 20 healthy subjects that are publicly available. And so here we immediately faced an issue that is one of the main challenges in biomedical applications, that is data scarcity. So many cases, having many geometries is really challenging. And so at first, we tried to develop tools and methods to address these issues. And the first one is try to reduce the size of the, so let's say, the variability of shapes by factorizing out some degrees of freedom. In particular, translations, rotations, and scale. So the good news is the physical problem is transition invariant, so we can, without loss of generality, center all the geometries. Similarly, since the physical problem is rotational invariant, we can align somehow the orientation in order to find equivalence classes between different geometries that are invariant with respect to, let's say, that are equivalent up to rotations. And finally, what about scale? The physical problem is not scale invariant, unfortunately, but still we decided to perform a per sample normalization in order to let the shape model focus on equivalence classes of shapes that are that differ just because of the scale. And then we appended the scale coefficients to the shape codes so that the surrogate model can be informed about the shape, about the size. So later I'll provide you a bit more details on it, but first of all, let me mention how we factorize out the rotations. Well, the idea is that we first of all perform an alignment of the basal plane of the ventricle. So we extract point of the left ventricular base, we fit a PCA model, and then we make so that the third principal component for the principal direction is aligned with the z-axis. And then we are left with the third degree of freedom, that is the rotation along this axis, So we extract the points from the right ventricle, we take the centroid, and we rotate it so that the centroid lies on the y is equal 0 axis. And on the bottom, you can see that thanks to these orientations, now all the geometries are consistent, and are also consistent between the two cohorts. Then, what about the way how we factorize out this scale? So as I mentioned, the idea is that we rescale all the geometries within the unit cube, and then we append the coefficients that we use for the rescaling, that is basically the size of the specific ventricle to the shapecodes. So in the end, the shapecode is comprises two subcodes. The first one informs about the size, and the second one informs just about the shape. So we have decoupled size and shape. And overall, in this way, we have reduced the complexity of the shape model, because we have reduced the variability of the shapes while still preserving the size information that will be later provided to the surrogate model. So how is training performed in practice? So we took all the ventricles. After performing these pre-processing steps, we generated a cloud of points by randomly sampling with high probability close to the surface in order to provide more accuracy close to the surface. And then we generate randomly initial guesses for the shape codes, and we train the shape model together simultaneously with the shape codes. So we backpropagate simultaneously through the weights of the neural network and to the shape codes. And in our loss function, we have first of all a data fidelity term, a second term that corresponds to the prior that we put on the shape codes that we assume to be sampled from standard Gaussian distribution. And third, we also provide a regularization term that controls the Lipschitz constant with respect to the shape codes of the TIP-SDF model. And in this way, we control the sensitivity of the sun distance function, and so the level set with respect to the shape codes. And this way, we promote a high regularity in the shape, in the Levin space. Then what happens when you have a new geometry? So in real life applications, we don't have a mesh at the beginning from the geometry. So we typically have the geometry represented, for instance, as a cloud of points belonging to the external surface. So the point is that we can leverage the fact that we are representing the geometries as zero level set. So we expect that the output of the sun distance function neural network when evaluated on the available points will be equal to 0. So our loss function will be simply equal to the root mean of the output of the neural network evaluated on the available points. Then, as a regularization term, we provide the Malanovic distance with respect to the empirical distribution of the shape codes obtained during the training. And after this inference step is performed, so we have an estimate for the shape code associated to the provided point cloud. We can now, thanks to the neural network, thanks to the neural field, evaluate the distance function in each point of the domain, and this can be used as an input to the marching cube algorithm to generate the mesh associated with this page. So by the way, we have in this way a way of automatically transform a point cloud into a mesh ready for computations. So we perform some tuning of the hyperparameters, and with this choice, so with the 16 shape codes, we got a reconstruction error that is always below 1 millimeter, which is good for applications. And also, we don't have significant correlations between the latent codes, which means that we are capturing variability without significant redundancies. And what happens when we have noise? So very often in real applications, we have noise in these point count representations, mainly because of the resolution of the imaging techniques. So we can still perform inference in a robust way simply by framing everything in a Bayesian framework. So the idea is that we represent its shape as a point cloud, that is in this case a noisy point cloud, and we consider our DeepSDF model as a generative model, where the probability of observing a given standard distance function, given the coordinates of the point and given the shape code, can be approximated by the Gaussian distribution, where the mean is given by the shape model and the variance is associated with the measurement noise. The prior will be given by the empirical mean and covariance obtained on the training set. And by doing that, we can write the log likelihood by using the Bayes theorem, where the log probability of observing that noisy point cloud given the shape code can be given when written as the sum of the log probabilities of observing zero standard distance function at the points belonging to the point cloud, thanks to the fact that the standard distance function, when evaluated on the surface of the domain, should be equal to 0. So by doing the computation, it turns out that the maximum likelihood estimator of the shape code is given by minimizing this loss function that is exactly the same one that we were using before, but where now we have an interpretation of the regularization parameters of the Malanobis term that should scale as the noise variance. And in fact, by doing that, we have a very robust reconstruction, even in presence of noise. So when the noise increases, the error increases, of course, but increases very mildly, and the reconstruction is robust also with respect to the number of points. So going to the physical surrogate, with respect to the standard architecture, we provide, besides the physical coordinates, also what are called in computational cardiology community as universal ventricular coordinates that are the solution of three Laplace problems that provide basically the optical basal coordinate, transmural coordinate, and circumferential coordinates. So as always, this is a positional encoding technique that allows to enhance generalization. And then, as I mentioned before, we perform this size shape decoupling by splitting the shape code between one part that is extracted in a deterministic way and the second part that just focuses on the shape that instead is learned by the shape model. And the output, of course, is the three components of the displacement field. So these were the first results that we got by using 35 patients for the training and 9 patients for the testing. So without providing any positional or geometrical information, we have a bad error on the training dataset. But if we provide positional encoding on even better shape codes, we can get a better error. However, on the testing geometries, the more information we provide, the larger the error is. So we have a significant overfitting, and this is clear also if you look at the training versus validation error over the epochs. So the model here is performing very poorly in generalization. And the point is that 44 geometries are not enough. So because of the strongly nonlinear response of the deformation and with respect to the variation of shape, 44 geometries are not enough to capture in order to train a surrogate model. And we were a bit disappointing by that because the shape model, on the other hand, was very satisfactory even by using 44 geometries. So we concluded that here the bottleneck was not in the shape representation, but rather in learning the physical response. However, this suggested that we could leverage this observation and exploiting the shape model in a generative way in order to generate new geometries that could be used to enrich the training dataset for the physical surrogate. So how can we use the shape model in a generative way? Well, the idea is very simple. We just sample in the latent space randomly by observing the empirical distribution that we had on the training dataset. And then, as mentioned before, we can compute the sign distance function associated with these hypothetical geometries, and then we can run the matrix cube algorithms to synthetically generate, without any effort, an arbitrary number of new geometries that are realistic. And in this way, we generated nearly 900 geometries. And by training, again, the physical surrogate on this enriched data set, we were able to reduce a lot the generalization gap. And so getting accurate results, so normalized root mean square error below 2% without having a significant overfitting. And I'd like to stress that this was obtained without adding real geometries, but just by using the shape code, the shape model that was already trained on the real geometries, and using these synthetic geometries to provide a stronger physical bias to the physical model. And finally, we also benchmarked our automatically extracted shape codes with PCA modes. So we trained another surrogate model where instead of using our shape codes, we used principal component analysis coefficients that we can get in this way. So we start from the cloud point, we evaluate on the computational mesh the universal geometrical coordinates, and so in this way we can interpolate the displacement, so the coordinates on a uniform grid that is the same for all the geometries. So we have a point-to-point correspondence between the geometries, and we can in this way extract principal component codes. However, as you can see here, with principal components codes, we have much larger, so we have a larger error on the training set, most importantly, a larger error on the test set. So we are less able to generalize. So we can conclude that thanks to the nonlinear representation of the neural network that we have in our model, we are able to extract a more accurate representation of the geometry. So to conclude, so we have proposed an architecture that allows to learn the solution map of PDEs in variable domains. This method is non-intrusive. It allows to use several different loss functions. Even physics-informed loss function could be used in principle. It's flexible as it allows for different encoding techniques. We have shown that by using universal coordinate systems, we can enhance generalization. And we have shown a couple of ways of automatically learn a shape encoding. One is based on conditional neural ODEs and works when you don't have variations in topology. And the other one is instead based on sign distance function. This is automatic, flexible, and accurate, as it can achieve comparable accuracy of the ideal situation when you have an explicit parameterization. And finally, in data scarce regime, that is very often the situation in biomedical applications where having many patients is a challenge. We can use a well-learned shape model in a generative way to enrich the observed physical domain for the surrogate model without requiring new real geometries. As future perspective, what we are now addressing is accounting for uncertainty, both in the shape reconstruction phase, so the epistemic uncertainty of the shape, and also in the surrogate model, so accounting for the error due to the imperfect surrogate. Then ways to promoting the regularity of the latent space in order to have a stable generative modeling, and also integrating this kind of architecture, so shape dependencies in other architectures such as latent dynamic networks. That this is an operator learning method that we proposed the last year in this a paper that achieves state-of-the-art results for time-dependent PDEs. So one extension would be to allow to include the shape dependency in this kind of architecture. So with this, I thank you very much for your attention. Just a small advertisement. I have several positions, postdoc positions in scientific machine learning, and both postdocs and PhD positions in cardiac modeling and inverse problems. So if you're interested on, anyone that could be interested, then feel free to reach out. Here you can find my email and my website. Thank you again. And if there are questions, I'm happy to have them. Thank you.
Thank you, Francesco. It's a really great talk and very cool presentation. If anyone has questions, we can ask a question.
Hi, Dr. Regazzoni. I'm Nikhil, and I'm a PhD student working with Professor Karnadakis.
Nice to
So I
meet you.
have a couple of questions. It was a really great talk. So first question I have is, so I'm wondering how this could be helpful when there is, let's say, presence of disease in the organ. And I'm just wondering because mostly in many of the biological applications we have, the geometric changes we are interested in are also like due to some biological phenomenon, let's say infarction in myocardium, and I'm trying, and it impacts cardiac output, right? So I'm just wondering if you can include, or do you have any comments on that? What would be the way of encoding when there is a presence of disease in the organ?
Yeah, so if I got your question, so when you have situations like an infarct in the organ, then there is also a space-dependent output. Yes, sorry, space-dependent input. That is the distribution of the infarct. That is something that we haven't considered here so far. So in that case, you will need some way also to encode this kind of input that can be done actually in several ways. So one could be to use some sensors, like is done, for instance, in the EPONets, and then we can use some position encoding technique to translate them from one geometry to another, or we can use other encoding techniques, for instance, based on autodecoders, like the one that I showed here, that are, I think, very suitable for handling situations when you have variability in the geometry, because you don't need to fix a priori, let's say, an encoding of the geometry.
I see. Thanks for explaining. I also one more question is, have you wondered about integrating metadata, maybe demographics, like the way you encoded the geometry using shape codes? So can you do that for maybe for like a patient's age or something like that, and include in the neural operator? Do you have any comments on that?
Yes, of course. Yeah, this is uh, already accommodated for in this architecture, in the sense that you can provide some scalar parameters that can be demographic information or others into the surrogate model. And this is what we are already doing, for instance, in the examples where I showed the left ventricle inflation. There we had two parameters, that was the tissue stiffness and the pressure. So everything here is still parameterized. So absolutely, yes, this can be done.
Great. Thank you. And I just have one last question. So when you share it, you use the shape codes, right? And you're using in a generative way. How do you ensure that your geometries are physiological consistent? I'm just curious because when you draw it, I'm not sure if like, do you have any comments on about the physiological consistency of your shape codes?
Yeah, this is a very good point. At the moment, we don't have any way to guarantee that we have a physiological consistency. So in the conditional neurology method that I mentioned, yes, this is granted for free since we have a diffeomorphism. So this allows to preserve topology and all the geometrical features. Instead, in the SDF-based method, the other side of the coin, since this allows for topological variations, that you cannot control them when you do generation. And indeed, when we use it in generative way, so this is something that I didn't mention, but and sometimes we ended up with the geometries with holes, and so we needed to exclude them, which of course can be done very easily by the Euler formula. Since you have a mesh, you apply the Euler formula, you can know if topologically this is a sphere or a torus, so you can easily exclude them. However, we had worked in order to provide a more stable generative model, and the inclusion of the Lipschitz regularization was done exactly in order to do that. So in general, the idea is that the smoother the map from the shapecode to the geometry is, the more regular, the more stable the generative model will be. And this is what I mentioned when in one of the final slide I mentioned that one of the future perspective would be to improve the smoothness of the latent space. And this is exactly in order to have a more stable generation.
I see. Thanks. That's a really great talk. Thanks for answering the question.
Thank you.
Thank you, Nikhil. I have actually two questions. One is a follow-up of Nikhil's first question. So if I understood correctly, Nikhil was telling about if the patient has a disease, then probably the material of the heart would be affected. So then probably you would need to learn the mapping from the constitutive relation of the heart walls to the stress or strain distribution, right? So right now you are encoding the geometry by training the encoding network to learn the sign distance function of the geometry. So why don't you directly try to learn the desired function in the complex geometry for the input case and the output case and learn the mapping between the latent codes of the input and the output function directly?
Yeah, so in case the constitutive equation varies from one patient to the other, then this should be somehow encoded into the surrogate model.
Auto decoding.
Sorry?
You could auto decode, right? Like you did.
Yeah, so the most straightforward way to do that would be to train a model that receives as an input some parameterization of the constitutive law. So if you have, say, n parameters in your constitutive law, you can provide these n parameters as additional inputs to the surrogate model. So in this way, you just learn the dependency between the parameters to the solution in a supervised learning framework. This, I think, would be the most straightforward way to do that.
Understood.
And once you have a new patient, you can also use this surrogate model to solve inverse problems if you want then to infer the parameters from a given deformation.
Thank you. My second question is like, is this related to the modulated implicit neural representations that came out in the computer vision a few years back? Like the geometry encoding part, is that similar or how different is it from that?
Sorry, can you?
The modulated INR, if you've heard of that, is that related to your geometry encoding neural
modulated
network?
INR, yeah. Yeah, it's strictly related. Indeed, this is based on an INR, implicit neural representation, and this is modulated by a shape code.
Understood. Okay.
So I think that modulated INR mainly refers to the architecture. Here we are simply doing a concatenation between the space coordinates and the codes. However, more recently, for other kind of test cases that I didn't show, we are using modulated INR as an inner architecture because, let's say, in more complex scenarios, then it has advantages. For instance, if you have the broad spectrum in the geometry, so you need to capture high frequencies and counteract the spectral bias, then could be interesting to use periodic activation functions and all. In this way, it's really convenient to decouple the space coordinates from the shape codes.
Thank you for answering the question. I think Professor Kaneda.
I have a question, Francesco. So there are many ways to encode geometry, especially parametric. But for example, transformers, called the Transolver Plus, and from Tsinghua. But there is a paper in Nature Computational Science by my former student Milan Gin with Natalia Andrianova from Johns Hopkins, where they did a diffeomorphic operator learning for hearts, for the physiology in the hearts. I'm sure you know that paper. So can you say a few things about the relative constant prompts of your method versus Daimon? They call it Daimon or Demon, D-I-M-O-N.
Yeah. I know this paper. I also know Ming Lang very well. So their method is somehow based on a linear type of encoding, in the sense that their encoding is based on two steps. The first one is to find the diffeomorphism between template geometry to the considered one. And to do that, they use LDDMM, that is an algorithm that allows to find a diffeomorphism. That is, however, not exact in the sense that it provides just an approximate one. And then they take basically the coordinates on a prescribed grid of this deformation that they learn, and to reduce the dimension, they use principal component analysis to do that. So in some sense, this approach is very close to what I before called PCA, with the difference that here we have used this universal ventricular coordinate to find the diffeomorphism. Instead, they used this LDDMM method to find the diffeomorphism. So that's the difference in the shape encoding part. Then in their paper, they use basically a DPONet for the decoder. And that's the other difference. I use a neural field, so an implicit neural representation, whereas they use a DPONet.
How many geometries did they use?
If I remember well, they had several hundreds of geometries.
Okay.
Yeah, that is much larger number of the ones that we used.
Okay, all right, yeah. All right, great, thanks.
I had a small question.
Yeah,
if that's fine.
Okay. Is anyone else going up? Okay, sure.
I think Varun started first.
Let Varun do it first.
Varun, yeah.
Yeah, hi, Francisco. So I had a couple of questions. The first one is about your geometric encoding part. So how does it, if you have like geometries which have like multi-scale features, like the example you showed where you had like holes in the plate, how well does it perform when you have like holes which are like very different in scale? And do you have any experience with things like that with your model?
Yeah, so we don't have direct experience with that. We never tested this kind of examples. What I can expect is that the model might struggle if we use simple fully connected neural networks as an in-M architecture, as I'm using here. So in that case, I expect that we should go for more specialized architectures that allows to deal with multi-scale, let's say with multi-scale fields. For instance, Fourier features or sirens or architectures like that.
Yeah, and also the other thing I was wondering was, do you see like any, I don't know how to describe it, but like when you use an SDF, you have to use the tolerance to actually capture the surface. So how do you like capture that surface accurately without any, waviness and other artifacts that show up when you use SDF?
But are you referring to a specific test case?
Maybe like, so when you have an SDF field around your object, you need to use a tolerance, right, to say that, okay, this is my level set sometimes. And when you see the output, you see that like it's slightly wavy because you said you have a tolerance around the level set surface that you created. So do you see like any kind of waviness in your output geometries?
So I don't think we need to prescribe a tolerance in the sense that at training time, we do train on the whole field, not just on the zero level set.
Yeah.
And then at inference time, so we consider just the zero level set in the loss function. And then when we generate the mesh, we use the Marchi cube algorithm that allows in principle to reach the exact zero level set, in the sense that you need to prescribe a mesh size, but you can converge to the exact zero level set.
Okay. What I was trying to, I guess, my question was actually, the network may have like values which are like slightly more or less than zero, but they may be a part of that geometry. So how do you like capture that accurately? And that is, I guess, what my question was.
So I'm not sure I got your point, but of course the shape model can feature values that are not zero at the surface because the representation of the shape is not exact. But as soon as it's able to find an approximate representation of the geometries, if it is approximate enough, then we are fine. But I'm not sure if that I got your point.
Yeah, it's just like when you have multi-scale features. If it is not very accurate, then you get higher error. I guess it was related to my first question.
Of course, if you have multi-scale features, then you need to train until you can capture them. There's no way. But yeah, I think that in that case, it's mainly about the architecture that you use for the decoder, for the SDF neural network. Because there are architectures that allows to account for this kind of issues. There is another technique that we actually used for the our TIC test case that I didn't mention, but we use it. That is to use a positional aware shape code, in the sense that the shape code is defined on a regular grid, and before providing the shape code to the neural network, we perform a linear interpolation within this grid. So the shape code is not shared by the whole domain, but it is a little bit localized in different areas of the domain. And this allows to, let's say, to go toward a more fine, a higher resolution in the description of the domain.
Francesco, I just wanted to say that Varun has a really good set of geometries for you. Probably the most difficult geometries I have seen that were given to us by Simula. So it's bottles, water bottles, non-parameterized geometry with water bottles. So he has a paper on the archive, so maybe you can look it up. Vivek, I suggest that for the interest of time, because we're already 15 minutes, sorry, Ruth Week, we move on and let Francesco, because it's Friday and he has to go to have a good dinner in Roma, there. No, in Milano. Sorry, Milano. So it's late. It's late there. But thank you very much for stopping by.
Thank you very much.
Yeah.
Thank you, Francesco, presenting your work. Maybe Jamin, are you here?
Hi.
Hi. Could you try sharing the screen, please?
Okay. Can you see my screen?
Can you go to the presentation mode? Yes, this is perfect. So I'll introduce you and then you can start.
Okay, thank you.
So the second talk, Jamin O would be presenting his work on 2 applications of separable physics-informed neural networks. Jamin works at the intersection of machine learning and numerical analysis, developing hybrid algorithms for partial differential equations and data assimilation. He earned his PhD in mathematical sciences from the Korean Advanced Institute of Science and Technology, KAIST, and is currently a postdoctoral researcher at Texas A&M University. With this introduction, I invite Jamin to present his work.
Okay, thank you very much for introducing me to everyone. And hi, I'm Jamin, a postdoc at Texas A&M University. So today I will present about my recent 2 applications of separable physics-informed neural networks, which I call SPIN or separable PIN. So let me explain what is SPIN first. So when there is a d-dimensional function f, SPIN just approximate such function f by representing it as R summation of separable function. And such separable function is represented by multiplication of multi-layer perceptrons, usually. So the audience may wonder whether there exists a theorem like universal approximation theorem, and the answer is fortunately yes. So in the original SPIN paper published in 2023, there is a theorem. So when X and Y be compact subsets of real numbers, then the set of SPIN is dense in the L2 space. So the last author, Professor Eun-byung-bak, now at Yonsei University, gave a talk at Crunch Seminar in 2023. So if you are more interested in what is SPIN, then I'd like to refer you to this previous YouTube video. So aside from the universal approximation theorem, the popularity of SPIN is from the notable speedups on regular grids. So for example, when the computational domain is d-dimensional, and let's say we have introduced n grid points per each axis, then the vanilla pin had the number of required forward passes for vanilla pin is n to the d. However, by exploiting the separable architecture, SPIN reduces the number of forward passes to n times d, which only scales linearly with respect to d. But here on the right side, I have included a short code snippet for actual implementation. So here the computational domain is 3-dimensional, and per each axis we introduced 100 grid points. So SPIN just represent the function as R summation of rank 1 tensors. So we introduced 3 multi-layer perceptrons, and then just compute using the Einstein summation API in NumPy package. So however, unfortunately, the speedup is not notable for arbitrary grids. So because of the speedup in regular grids, there have been many variants out there. So one straightforward extension is extension to operator networks. And we may consider physics-informed machine learning framework for separable operator networks. And recently proposed Kolmogorov-Arnold network type can be used for instead of MLP. But today I'd like to introduce my application to the Boltzmann-BGK model. So here, Boltzmann-BGK model actually simulates dilute gas dynamics. Because the dilute gas does not follow the fluid dynamics law, Boltzmann-BGK model simulates gas dynamics from evolutionary dynamics of particle density function. So the governing equation looks like this one, and as you can see, there are two notable operators. The first term is transport term along the x-axis, and the second term is relaxation term. And you may consider this relaxation term as an approximation for the quadratic Boltzmann collision operator term. However, it actually steers the particle density function towards the thermodynamic equilibrium. And here, Knudsen number Kn describes how the gas is dilute or not. So for example, when Knudsen number is 1.0, it means that the gas is pretty dilute, whereas when Knudsen number is 0.01, it means that particle is very dense. So when Knudsen number is big, the dominant dynamics is transportive behavior. And when Knudsen number is small, there is also transportive behavior, but yeah, the solution profile is much more smooth on the left panels. And I'd like to mention that the first connection between PIN and BGK model was published in JCP 2021. So yeah, let me introduce why I am interested in this simulation. So the BGK model is computationally expensive because of its high dimensionality. So because it simulates it simulates particle density function defined on a velocity domain. So there are 3 additional computational dimensions for the model. So when we are considering d equals to 3, the total dimension is up to 7, including time. So classical method is often very expensive. And yeah, when we are computing the Maxwellian distribution MF, we have to compute the zeros first and second moments of the particle density function F. So the zeroth moment is called macroscopic mass, and U is velocity, and T is temperature. So actually, the Boltzmann BGK model is integral differential equation. So yeah, because of the presence of integral, the computation is expensive. And also, because the BGK operator steers the particle density function towards Maxwellian distribution M, and Maxwellian distribution is basically Gaussian density function whose mean is U, and covariance metric is T times identity matrix, and the total mass is rho. So the first challenge comes from the high dimensionality and the presence of integrals. So it must be related to high computational cost. And the second challenge was from the presence of integrals and the fact that the solution resembles Gaussian-like density. And it is related to generic kinetic equations, and it hampers the accuracy of S-spin prediction. So to overcome the first challenge, yeah, let me explain the related computational cost issue. So when we compute moments of the particle density function F, we have to compute this triple integral, right? So the standard way to compute this triple integral is doing quadrature rules, tensor product of quadrature rules. So we just compute F defined predefined velocity grid, and then computing the moment, approximate this integral by 3 nested for loops. So the computational cost for these moment computation scales like n to the cube. So when we double the number of quadrature points per each axis from 65 to 129, the associated computational costs increases more than 5 times. So, and for the extreme case, like when n is 1,000, more than 1,000, it ended up producing an out-of-memory error. However, when the f is represented by an S-spin, then we can do actually much better than this. So we first represent f by S-spin representation, and then by exploiting the fact that the moment integrals are linear. So we just interchange the order of summation and integration. So by doing so, we can reduce the computational cost to 3 times R times N, because it is just actually summation of 1D integrals. So in this table, as you can see, as we double the number of quadrature points n, the computational cost increases not that much. The reason behind is that I included the forward pass computational time. So the increasing the amount of computational cost is not notable. And notably, for the extreme case, like when R is more than 1000 and N is more than 1000, it does not produce any out-of-memory error. So by doing so, we achieved at least five times speed up, and this separate integration strategy is very memory efficient compared to the standard way. And the second challenge is related to tail error accumulation. So if you see the left panel of this figure, so you cannot see any issue, right? However, when we see the right panel, we can observe that there are some artifacts in the blue curve and red curves. However, it just shows initial condition. However, the initial condition loss is less than 10 to the minus 12. So it means that in absolute scale, the F0, the initial condition is well approximated by S-pin. However, when we compute moments, the errors in tail, when V is large, the absolute scale is very small. However, the small errors in those regimes can be amplified through the integration process when computing the high order moments, for instance, first or second moments. And due to the hyperbolicity of the BGK model, the small error does not decay as time goes on. So it tempers the prediction accuracy of the BGK model. So approximating the initial condition very well is very important issue to ensure that S-pin captures the underlying solution accurately. So to validate or remedy this claim, I have conducted a toy experiment where approximating this standard normal Gaussian function with an MLP using mean square error loss. So on the below figure, the blue curve shows the results for approximation. And the left panel shows point-wise relative error. So as you can see, if when V goes from 5 to 10, the point-wise relative error increases very fast. And the right panel shows the relative error for second moment computation. And as you can see, when we enlarge the truncation parameter large V, the second moment accuracy increase in general. And sometimes the relative error exceeds 10 to the minus 2 level, which is not very desirable. So to solve this issue, I make the neural network output decay as fast as Gaussian. So I just multiplied this Gaussian-like function to neural network output f theta, where I let tau and mu be learnable parameters as well. So during the during the training procedure, the tau and mu adaptively chooses the position and the shape of Gaussian-like networks. And the second remedy was imposing large weights to faster particles. So when we compute pin loss, it is actually formulated as a mean square error, right? So instead of considering uniform weights for each collocation points, I considered weighted average, where the weight is inversely proportional to the magnitude of f theta. So in the first remedy, I already made that f theta decays as fast as Gaussian. So when V is large, the magnitude of f theta is very small. So the rate is big for large V. So after the right figure shows the S-pin output before and after introducing these two remedies. So before the introduction, we can see that there are large deviations between the reference solution and neural network approximated solution. However, after introducing these two remedies, the deviations are not notable, and the solution accuracy was about 10 to the minus 3 in relative L2 error. Yeah, so having these having these methods, here I am presenting 2D simulation and 3D spatial dimensional simulation results. So these are classical Riemann problems where the initial condition is smooth version of discontinuous functions. So in the 2D case, the computational domain is square, and in that square, there is a circle. So inside the circle, the gas density is high and the temperature is high also. And the BGK model sees how the gas propagates in time after removing this circle. So S-pin solution captures the reference solution very well, where the errors are about 10 to the minus 2 level, and the total training time was about 5.5 minutes because of the fast inference time for S-pin. And the below movie shows an analogous results for the 2D case where we replaced circle to the sphere. And the total training time was 50 minutes, and errors, the relative errors are about 10 to the minus 2 here. So for the extension of this application, I am planning to do some error analysis by using well-established kinetic theory and approximation error analysis for neural networks. And it might be possible to solve inverse problem within this framework, such as estimating the Knudsen number of experimental data. And because the second challenge was related to generic kinetic equations, so this framework can be applied to solve more diverse kinetic families, such as full Boltzmann equation or Vlasov-Poisson equation. So as a preliminary result, I brought my results on Vlasov-Poisson model, where Vlasov-Poisson model simulates sometimes plasma. So the governing equation looks very similar up to the second term. However, there is no relaxation process, and there is transfer term along the V direction. And the coefficient for the transfer term along V is computed by taking the gradient for the potential function phi, where the potential function phi is the solution to the Poisson equation, where the right-hand side is self-induced. So here is the solution profile computed by S-pin. So I computed the solution up to time equals to 2.4. And I haven't measured the accuracy of S-pin solution. However, the Vlasov-Poisson model has to conserve the total mass in time because the computational domain is periodic. So I computed the mass over time for the S-spin solution. And based on the observation, the total mass was conserved up to 2 digits. So I am thinking that the S-spin solution is accurate up to 2 digits, maybe. And the reason I was doing is that in June, Professor Yeonjung Shin at North Carolina State University presented thermodynamics-informed LASTI framework at Crunch seminar. And in that video, he mentioned about whether PN can solve this Blasov-Poisson model well or not. So I was wondering whether SPN can solve this or not as well. And based on the result, I think SPN can capture the underlying solution very well and efficiently. Yeah, so this was my first part of the presentation. So maybe if any, I am happy to get some questions from the audience.
Yeah, I mean, I have a question. We also have implemented S-pins and so on, and I was wondering if you have seen a case where a spin is not so accurate for non-separable solutions, strongly non-separable solutions.
Yes, I think this solution is non-separable. So, but when I was approximating this kind of smooth solution, the R parameter was set to about 100. However, for getting more accurate solution for this kind of complex profile, like discontinuous solution, I have to set the rank parameter R to more than 200. So
Okay, yeah.
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 So as long as the number of basis functions are enough, then I think SPin can approximate various ranges of solutions.
Yeah, Chanshi, I don't know if my student Chanshi is watching, but basically, I think she had some issues. Chanshi, are you here? Chanshi Wu? Maybe not. Anyway, she can ask later. Maybe
Okay.
you can proceed with the second part of your talk, yeah.
Okay. Thanks for asking me a question, and I'll proceed to the second part of my application. So yeah, after applying SPin to BGK model, I have applied SPin to data assimilation problem. So let me first explain what is data assimilation problem. So many scientific phenomena can be modeled by an evolutionary equation where the governing dynamics is F here. And we have to simulate such dynamics, we have to specify what is U0, the initial condition. However, we often do not know what is exact U0. For instance, let's say we are interested in predicting weather of tomorrow, then we have to put some atmospheric condition to the prediction model, right? However, satellite observations or automatic weather system cannot can measure some atmospheric states. However, the measurements are often very sparse and noisy, so we may say that we never know what is true initial condition. And yeah, some atmospheric dynamics is very sensitive to initial conditions. So when we slightly perturb the first component of the initial condition by 10 to the minus 3, and after integrating the dynamics up to time equals to 1, the solution is totally contaminated by the initial small perturbation. So this one is the result from the famous Lorentz 96 model. And because of such issue for chaotic system and the absence of exact initial condition, we can say that better or much more accurate initial condition estimates can be used for better, accurate predictions. So data simulation is basically estimating the true system states of the evolutionary equation. So we have observations in one hand and physical principles described by differential equation on the other hand. So actually there are already many algorithms out there. The most famous one is variants of Kalman filters, and the nonlinear counterpart is particle filters and recently proposed square filters from the Oak Ridge National Laboratory. And we can consider variational methods as well. For instance, and these variational methods actually estimate the maximal point of the posterior density function. And because of the presence of large data set, recent ML-based variants can be used as well. But in this talk, I'd like to only focus on 4-dimensional variational data simulation algorithm, which I call as 4D bar. So here, 4D bar is basically a PDE constraint optimization problem or differential equation constraint optimization problem, where Y is observation obtained by applying observation operator H to U and then adding random noise epsilon. And because observations are direct measurements of the true system state, partial and noisy direct measurements of the true system state, the accurate initial condition must be compatible with such observations. So here, this functional J measures the discrepancy between prediction and observation. And here, UK is computed by simulating underlying evolutionary equation from time equals to 0 to time equals to tk. So because of the nonlinearity in solving the evolutionary equation, so the minimization procedure requires iterative approach. For instance, gradient descent based one. However, computing the gradient requires computing gradient through the differential equation solver, which might be very expensive. And also, this problem might be ill-posed. For instance, when the governing dynamics F is diffusive, then there might be multiple solutions for this problem. So for instance, when there is a small error in U0, this error can be decay very fast because of the diffusive term in PDE, if there is. So because of such issues, I considered an alternative formulation through PIN. I call this framework as PIN 4D bar. So the crucial difference, the major difference lies in how we inverse physical constraints into the optimization procedure. So the vanilla or classical formulation inverses physical constraints through the differential equation solver. However, in PIN 4D bar formulation, I incorporated physical constraints through the pin loss. Because pin can predict any the system state for any spatial temporal location. I mean, the input of the pin is usually t and x coordinate, right? So we can actually produce any spatial temporal system states. So this pin formulation enables parallel in time optimization. So we may expect that this alternative formulation can speed up the compared to the original formulation. So to assess the efficiency of this alternative formulation, I have considered 2D homograph flow as a benchmark problem. And it is just an incompressible Navier-Stokes equation with a specified forcing term. And because of the incompressibility, it admits a vorticity form. So we actually computed the reference solver. I mean, the governing dynamics is vorticity equation. However, we assimilated the velocities, the observed velocities. So for the reference solver, I considered 256 square reference resolution and 10 to the minus 3 times stepping size for the temporal integrator. And yeah, the reference solver was implemented in JAX-CFD package. And for the observations, I considered noiseless case and linear observation operator H. And the observation time points were from 0, 0.05, 0.5. And here H is a uniform downsampling operator. Yeah, just sampling from the reference resolution to 8 square. So the downsampling ratio is about 32 per each axis, and we are using just only 0.1% of the total degrees of freedom. Yeah, so here is the result. So for the first row presents estimated initial condition. And with this estimated initial condition, I produced forecasts up to time equals to 5.0. So as you can see, pin 40 bar estimated initial condition is very close to the ground truth, whereas vanilla formulation produced estimates which has spurious oscillations. And the vorticity features are preserved well compared to the vanilla initial estimates. So in computational perspective, the total execution time was reduced by 88% compared to the classical formulation, and the relative L1 error for the initial condition estimate was reduced by 78%. So in total, I would say that this S-pin 40 bar formulation successfully accelerate the computational issue in the vanilla 40 bar formulation. But the interesting thing is that pin 40 bar formulation actually produced a smoother solution without spurious oscillations compared to the vanilla vanilla 40 bar algorithm. So this was a pretty interesting part, and I could not fully understand what's going on there, but one possible explanation might be related to spectral bias acted as an implicit regularizer. So here my claim is that pin 40 bar formulation exploits the spectral bias, which has been considered as a bottleneck in accurately approximating the complex profile in no data regime. Yeah. And the Hints paper actually first explored spectral bias can be exploited to accelerate classical numerical solvers in terms of neural operators. So another surprising point is that practical implementations of Bolivar. For instance, ERA5, which is the state-of-the-art from the ECMWF, uses 3 nested grid resolutions for their implementation for the Bolivar algorithm. So the reason is that multi-grid methods. So it is basically multi-grid methods, and the intuition behind multi-grid methods is that the coarse-grained solver captures the low frequency feature fast, and the progressive refinement procedure helps capturing high frequency details further. So to validate whether spectral bias played a key role in smoother solution produced by P in Bolivar formulation, I conducted small experiments by just parameterizing the initial condition with spin. So here, J neural is just parameterizing only the initial condition and leave the rest of the part of the algorithm the same. So this figure shows the result for the toy experiment, and here the red curve shows the result for the vanilla formulation, and blue curve shows the neural formulation. And in panel A, we can see that both methods decrease the cost. And in the panel B, the vanilla formulation actually increased the L1 error, whereas neural formulation decreased the error. And panel C shows power spectra for the initial condition estimates at iteration 0 and iteration 1000. Oops, sorry. So after iterating 1000, we can see that the vanilla formulation actually injects spurious energies in high wave number regimes. So we can say that increased energy was the cause of why there was spurious oscillation in the initial condition of the vanilla Bolivar formulation. So here are the overall results. So in this figure, I have included another method, which is called hybrid in the first column. And the hybrid method is basically combining pin and neural. So we first estimate the initial condition by pin, and followed by 500 times of neural Bolivar minimization procedure. So here is the rollout accuracy, the prediction accuracy test. So overall, there is a tendency that L1 errors decreased initially, but increased afterwards. I don't know why the error decreased initially. But the interesting part is that for the initial condition accuracy, PIN was more accurate than neural. However, for forecasting accuracy, PIN was worse than neural formulation. One possible explanation for this crossing is that the neural formulation directly uses the reference numerical solver when minimizing the prediction observation misfit. So this is inherent advantage of neural formulation over PIN. So there might be one explanation. And overall, the hybrid method achieved the smallest accuracy, smallest error among all the considered method. And I'd like to highlight other advantages of PIN formulation. So as I mentioned before, parallel in time optimization and fast spin architecture successfully reduced the total execution time by 88%. So pin formulation is very fast compared to the vanilla formulation. And actually there was a paper published in 2025 CISC where they combined parallel algorithm and Fodiva formulation to enable parallel in-time optimization for the classical vanilla Fodiva algorithm. Yeah, however, I think this is still in early stages, so I have not compared this method to pin formulation. And the second advantage was robustness against noisy observations. So on the right table, I corrupted observation with 5% noise to 25% noise of Gaussian noise. And yeah, the other methods could not produce reliable initial condition estimate at all. However, the alternative formulation, pin Fodiva, produced accurate initial condition estimates compared to all the other methods. And in the context of machine learning-based methods for data assimilation, the pin Fodiva formulation does not require any ground truth data. So this formulation might be very useful for when there is no pre-existing data or the data is very scarce. So as future works, I'd like to apply this method to more realistic settings. So one of my main motivation of this work was to apply to this framework to numerical weather predictions. So if I'd like to do that, then I have to consider sphere geometry to yeah, because the global weather prediction is defined on the globe. And because observations have noise, and sometimes we are not sure about whether our evolutionary equation is correct or not. So incorporating such data uncertainty and model uncertainty to enhance the accuracy for the initial condition estimate would be a very valuable direction as well. And for numerical weather prediction task, the most popular governing equation is primitive equation. So in this case, I'd like to test whether SPIN can solve primitive equations well or not. And of course, further comparisons with more realistic and practical Fodiva implementation would be interesting also. Yep. So here is the summary. The main takeaway is that separable physics-informed neural network is very fast on regular grids. However, on the arbitrary grids, the speedup might be not notable, so be cautious about that. And for the first application to BGK model, SPIN enables a faster moment computation by exploiting the separable structure and just interchanging the order of summation and integration. And for the application to Fodiva algorithm, SPIN exploits the spectral bias so that the estimated initial condition was much more smoother than the vanilla formulation. So my talk was based on these references, the original SPIN paper and SPIN BGK paper published in CISC 2025, and my recent archive, my recent archive preprint. So this is pretty much everything I brought today, and thank you for your attention, and I'm happy to take any questions from the audience.
Thank you, Jamin, for presenting. Do we have any questions from the audience?
Oh,
Hi, Jamin. I had a quick question. I'm a PhD student at Brown. Could you give
Hello.
a bit more intuition about how the 4D war works? Like,
4D estimates initial condition by minimizing the we first there must be some initial guess for the initial condition, right? So from that initial guess, we put this initial guess to the numerical server to generate some predictions. And then we apply observation operator H to generate it prediction, and then measure the discrepancy between simulated observations and real observations. And then minimize that discrepancy. This is how 4D works in general.
I see, I see. So here, like, you're not assuming any knowledge about the covariance or anything of the noise epsilon that's being added to the observations, right?
Yeah, so if we take more generic approach, then there must be some covariance metrics in this norm. However, for simplicity, I have omitted such things.
Okay, all right. So you're just minimizing the error between the observation and the predicted observation.
Yeah, exactly.
Okay, all right. Thank you.
I have a question. Yeah, thanks for nice talk. I'm Young Lee, a postdoc working with George, and nice to see you again in this seminar.
Hello.
And I'm just curious about the hybrid method. That what is the advantage of the hybrid method? Because usually, actually, the main idea of the hints is using the classical solvers as the high frequency remover and use the neural operator to remove the low frequency part. But in this scenario, I'm not sure this hybrid method can work something like that, or can accelerate or get advantage from other method.
The major motivation for this hybrid approach is that so pin execution time is the computational cost for the pin formulation was low compared to the classical formulation. So I just wanted to produce the best initial estimate by combining these two, pin and neural, much faster than the classical formulation. So I just took 10,000 optimization steps for the pin method first, and then followed by 500 descent steps for the neural to produce the hybrid initial estimate. So total execution time is 300 seconds, and which was far below than the classical formulation and neural counterparts. So I just wanted to showcase that pin formulation can serve as a fast initial guess for vanilla methods or neural formulation.
Have you ever tried the alternating approach? Just maybe small number of pins and small number of neurals and small number of pins and small number of neurals, like alternating approach?
I have not considered, but it might be very interesting to pursue in that direction as well.
Okay, then thank you so much.
Thank you.
Thank you. Do we have more questions for the speaker?
Maybe a comment. The minimization problem for the data simulation is similar to a paper that called H-pin, hard constraint pins, that Lulu published with Steve Johnson from MIT, probably in 2022, maybe around that time, maybe 2021.
SIAM review paper, right?
SIAM, not SIAM review, it's a SIAM CISC, it's a CISC paper
I see.
called H-pin, hard. It's basically a similar type of constraint. So you have like a minimization, let's say minimize the energy, let's say, of a system, plus subject to the PD. Just like you had the trajectories subject to the PD. And they use augmented Lagrangian to do it very accurately. Yeah.
All right. So I think pin formulation. So I think pin is very good for such PD constraint optimization problem because of the inherent spectral bias, it produces the simplest solution, I guess. So
Yeah.
And yeah, in here, time parallel in time framework, parallel in time advantages is of course very good compared to the classic formulation. So yeah.
Yeah. No, they were solving a steady Stokes. So it was not a data simulation in time. It was just a same type of formulation. You try to minimize something, right? Like your J subject to a PD constraint, let's say.
Right.
Yeah.
Okay, I will of course take a look at it.
Do you have any other questions for Jamin? If not, I'd like to thank Jamin and Francesco once again for presenting their works. And I hope you have a good weekend ahead. And with that, I would like to close this week's Crunch Seminar. Thank you.
Okay, thank you for having me.
Thank you.